Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Space Pilot, published in 1984 by Kingsoft, coded by Henrik Venning. This was, of course, a conversion of the arcade Time Pilot. I remember both of these games very clearly when I was very much younger than I am today. I'm going to convert the TAP file to a single PRG file, program file, so I can then load the program file into C64 Debug GUI, and then we can start to have a look at the rendering. Starting to load the TAP file in ICU64, and I can see that there's data in the tape buffer in memory already. So standard procedures here. Let's just double check to see what's in the memory. Looks like it's machine code. So standard procedure. We'll just put a very large ranged breakpoint in the start of memory. We'll continue on in the normal tape loader, and then we'll see what it does. There we go. It's the standard kind of way of starting to execute at 351. If we use the CPU history command, it's jumping through that indirected vector there at 300 in hex. And this is a pretty much standard way of auto-running a tape turbo loading piece of code. It's taking quite a standard approach. It seems to be reading a byte, and while it's equal to 0, it just loops around, and that's probably the turbo data header information. It seems that it's reading 4 bytes, storing them into C1, C2, 2D and 2E in hex, and then it just seems to be repeatedly fetching bytes and then storing that into an indirected address. We've got some JSRs into what looks like the basic ROM and also the kernel, so it looks like it's doing some tidying up in terms of vectors and then running some kind of like basic start routine or basic continuation routine. So it's probably going to run a very simple basic program after it's loaded all of this tape turbo data. Yeah, there's just some timing code here in the rest of the tape buffer, which is related to the tape turbo data load. It's just using a standard approach of using timer-based byte recovery, or byte reading rather, from the tape. Yep, 2D in hex is 45 in decimal, 45 and 46 is one of the 0-page memory locations that's commonly used for, say, for example, the end of a basic program. FC93 in the kernel, FD15. If I remember correctly, these are restoring vectors to their default state. We'll see what happens after it's finished loading all of this tape turbo data. There's no kernel activity, you see, in terms of executed code. It's just executing code at the beginning of memory. And that's those blue pixels that you can see in the memory debug event view there. And there we go. It's got to JSR FC93. FC93 is going to be, if I remember, let's have a look, it's going to be restoring vectors or something like that. FC93, ding dong ding dong ding. Yeah, a switch from cassette IRQ to default IRQ. Yes, so it's restoring those IRQ vectors. Cool. And then the next one, FD15, is restoring IO vectors. Okay, so it's just doing a double belt and braces approach to making sure that the vectors are back to normal after the turbo tape load. There we go, initialize vectors, more initialize vectors stuff. So it's doing lots of vector reinitialization, right? And restoring from tape mode IRQs to normal IRQs. It's doing a clear command. So that jump, or JSR rather, into the middle of the clear command, once you have the basic start and end 0-page memory location set up, which 45 and 46 in decimal, were updated by the tape turbo loader, right? It just makes sure that the basic program in memory is correct and all of the other zero-page memory locations related to basic execution are also correct. It's the first step that you would normally do on the path towards executing a basic program. I can see there that there is a sys2061 command at the start of normal basic. So I have a pretty safe assumption here that this last jump at A7AE, which is the middle of the next command, if I remember rightly, it's one of the ways of doing basic start anyway. So once you have a basic program in memory and you're not going to execute run from the keyboard buffer, what you can do is that you can fool basic into starting your program. So you just need to do these little fix-up routines. You clear the end of memory, well, you do the clear command, make sure that the variable zero-page memory locations are correct and everything else, and then you go into the next, and so on and so forth. And then it basically starts execute the basic program. There doesn't seem to be much loaded beyond 6064 is the next screen, 6C is the screen after that, and then 68 and then 6C00. So yeah, there doesn't seem to be anything else loaded in memory. So what we can do, theoretically speaking, right, if this is going to be the start of the game, let's see what happens. So we'll just save out some memory, right, because we want to convert this into a PRG file because C64 debug GUI doesn't run, or at least my version doesn't run, tape files or tap files. I think it runs T64s, but it doesn't run TAPs. Anyway, so we'll just save out this whole chunk of memory, starting at 801 in a hex and ending at 6C00. It was 6C00, right? Yeah, that looks like the start of some kind of like decompression or memory movement code, right? Yeah, okay. So yeah, it's not accessing the basic start and end memory addresses or zero page. Right? It's not assuming that zero page memory locations are set up correctly, which is an added bonus because I might want to compress this later on. So it's not assuming that the end of basic memory is correct, like some decompressors or some memory movement pieces of code do, right? Which is annoying because then you have to make sure that 43, 44, 45, and 46 in decimal are all set up correctly. Oh, that's interesting. So it's not quite getting into the game. Look, it's prompting for press play on tape again. Okay. So even if I try and compress this, it's not going to do the set. It's not going to do. Yeah, look. Okay, so there's that 69 sys2061. Line 69. Okay. Anyway, I wonder if that was deliberate. Maybe. Anyway, back to the code. Right. So it doesn't look like it's loaded all of the data for the game, does it? It looks like it's doing stuff. So let's put a breakpoint, large ranged breakpoint, and then let's see what that. Yeah. So it's definitely starting that code, right? Through the basic start stuff, but oh look, so it's doing a bunch of memory moving, and then it seems to be doing FFBA, JSR to FFBD, and JSR to FFD5. If you remember your kernel functions, then you'll remember that this is set file name parameters, and then it's going to be set LFS, and then it's going to be load, right? Set nam, set LFS, and then load at FFD5. So then it's going to go and load some extra data using the kernel loader again, apparently. Okay, so it's done some memory shuffling around, and then it's going to load some extra stuff. So after the load, it's going to do an RTS. So it's doing a JSR, then an RTS. That's certainly one way of doing it. You could have done a jump. And then let the RTS inside the kernel return back to the subroutine. But anyway, we'll continue on. We'll see how this goes, and then we'll see where it returns to. So we're currently at 872 in hex. Oh, okay, so it's returning back into a subroutine, back into the kernel, but we're in the wrong bank. Let's go back into the CPU bank. There we go. So E147 is probably the return from, return from a sys command, which is not a surprise because it did. It executed sys061, right? So yeah, okay. So let's put a breakpoint, another large range breakpoint. And oh look, it's returning back into the tape turbo loader. And actually the tape turbo loader is then expecting to load the next bunch of data. Okay, well, that's fine. So it's doing 2 tape turbo loads now. Interesting. Okay, so it's turbo loading a whole bunch of extra data now. Oh, now it's done the memory shifting. It's loading more stuff. Okay. And look, there's a sys24320 in decimal. So what we'll do, I think we'll put a ranged breakpoint now between 400 in hex and A000 in hex. Does anyone call it A1000 when you're referencing hex numbers? Because, 400 in hex, right, and A1000 in hex kind of makes sense-ish. Anyway, look, it's using the same basic start routine again in the tape turbo loader, but it's probably going to start executing at 24320 in hex. Yeah, that's the wrong memory command. There we go, mistyped. Let's put decimal for 24320. Yeah, okay, so D8A205A900, that's machine code. Clear decimal flag, yeah, there we go. Clear decimal, load X, load A, yeah. So it's starting to, okay, so I think this is starting to execute the game, right? So 5F00 looks like the main game entry point. So if we want to convert this to a PRG, let's go back and save out the whole of memory again, but this time we'll make sure that we'll include the correct start address at 5F00. So there we go, we hit that breakpoint at 5F00. So now we'll just set the bank to RAM again. We want to make sure that we save out the whole of memory, I think, because the whole of memory looks like it's been roughly sparsely loaded into. So we'll just do the whole bunch of memory from 200 in hex all the way up to FFFF, I think. Oh, well, look at that. There's some superfluous information there. Look, there's a screen. Look, transfer 400, 800 to 3800 and transfer D800, DC00 to 3800. That's interesting. Oh, so it looks like there's, copyright 1983, H. Venning. And then it looks like there's some bunch of screen data there. Yeah, it looks like there was a machine code monitor or the remnants of a machine code monitor screen right there. Interesting. But, not entirely useful. Anyway, so let's just make a note of what 0 page of the processor port is 0 page memory location 1, which is on the 6510 processor. The processor port, which is important because it tells the processor, or tells the system rather, what memory banks to bank in terms of basic kernel, I/O space, etc., etc. So we'll save out another attempt at converting this into a PRG, noting down the memory start address and also noting down the processor port value. We'll save it from 200 all the way up to FFFF in hex. There we go. And now let's go to my Commodore 64 tools binary directory and, wrong command, LZMPI. There we go. So LZMPI is my compression tool. We will use the 64 basic start compression options with the U option, which is the probably the better compression option to use. It's really quick to decompress and it also gets very good compression. we won't use the V option because that's incredibly involved compression, and it takes a very long time to decompress. So that's usually not very usable. It's usually used for 1K demos or 4K demos at most, because it takes ages to decompress. Anyway, so we will need an output file, so we'll just call it ctemp space pilot.prg, and there you go, input file and output file. We want the we've already set up the processor port to be 27, which is what it was, and then the entry point at 5F00. Now let's give it that a try just by running the PRG file, and it should open up a new emulator. The B option flashes the border, and there we go during decompression, and yeah, looks like the game perfectly works from the newly created PRG file, from the tab file. So now we can load the PRG into C64 Debug GUI. So here we are in C64 Debug GUI, and don't forget, as usual, I'll put a link to the tools that I use in the video description below, so you can also see how these tools are used. But straight away we can see from this debug screen view here that the red bounding boxes indicate where the hardware sprites are, but interestingly you'll notice that the bullets, the enemy bullets and also the player bullets when I shoot, but also the enemies they don't have red bounding boxes, right? Which indicates that they're either characters or bitmap. And in this case, I can see that it's using a bitmap screen, a multicolored bitmap screen. I can see, look, we can see where the sprites are. We can see what the sprites are, rather. They're clouds, the player, and also the guy in the parachute, or the person in the parachute, I should say. We can see that there's no sprite multiplexing going on. There's no screen. Well, okay, so the game's paused, but I didn't notice any other bitmap offset being used during the screen frame advance. There we go. So yeah, okay, so I can see here, look, from the memory writing or the memory access indicator, that it seems to be doing a sparse draw. We'll verify that later on in ICU64. Let's look at a larger memory map there. So so when there's no enemies on the screen, look, there wasn't anything being accessed in memory, but now there's tons of enemies on the screen. That memory for the bitmap is being heavily accessed, but it's being accessed sparsely. It's not wiping through, or it's not touching through all of the memory on every frame. So it definitely looks like there's a sparse redraw going on, or an erase and then draw, probably erase and draw. We'll check that later on in the code. But yeah, very, very nice, right? I mean, so the clouds in the debug view, the clouds appear in front of the score panel on the right, but the score panel on the right actually obscures the clouds in the real C64 view. So that tells us that the sprite priority, those clouds are set to be on the background. We'll just check that when we go back into the game. C64 Debug GUI has now locked out all of my keys. I'm going to have to restart it. One moment, please. So here we are back again in C64 Debug GUI. Notice the clouds in the debug view are in front of the score panel, but the clouds on the real view appear behind the score panel. So this tells us that the hardware sprites have priority, which is behind the solid black of the bitmap score panel there. So the bitmap score panel is going to have a solid black. And so actually the background is transparent and it's blue on this, which is an intriguing way of doing it, but it's a very good way of doing it. You'll notice that the hardware sprites, they are expanded for the clouds at least, and they tend to have a little weird kind of like clipping issue on the left hand side, and that's because the hardware sprite coordinates for the left hand side of the screen with expanded sprites needs to be tweaked slightly, but I guess the programmer didn't know that at the time, so they didn't apply that tweak for the a safer transition of the scaled sprites on the left-hand side. Anyway, so we'll have a look at this in ICU 64 now. That text screen there is going to be the bitmap data, but there we go. There's the main game screen. In terms of bitmap screens, we've only got one bitmap screen. Let's expand it. And let's see if we can find how this game draws its bitmap software sprites. We call them software sprites because they are sprites updated by the CPU. And in retro gaming vernacular or terminology, if you like, that's why they're called software sprites rather than hardware sprites. So we seem to have this routine here, which loads from data at A4, whatever, A4 something something in hex, and then a couple of nots and an OR and then a store indirected. So I'm guessing that the 2735 and 2736 are no op instructions, but I'm guessing that they get updated by something else. We can see that the indirected memory location at 30 and 31 is smack bang in the middle of the bitmap data somewhere. So we know that this routine, so we know that this routine is being modified by storing over the top of those no-op instructions, and there were two of them, 2 bytes next to each other. Look. So the code got changed. So instead of no-ops, there's an EOR with an immediate value. That's an intriguing EOR as well. EA is an intriguing bit pattern. So it looks like the same routine is being used to either erase or in sprite data into the bitmap data. This is a very standard way of erasing and drawing data into a bitmap when you want to render software sprites. What is a little bit unusual is that the same code seems to be self-modified into making it an erase or draw, because when you EOR it with FF, look, EORing it with FF takes whatever data was there and inverts all of the bits, and then you're turning it into an AND instruction rather than an OR instruction, and then this basically unmasks and sets all of those bits that you did set back to 0 again by inverting the data and then masking it out. So the game is calculating at runtime effectively by using the EOR and AND. It's calculating the inverse mask data from the sprite data, I'm guessing, software sprite data, and then it's masking it out from the bitmap, and then it's erasing that. So it's almost certainly, I'm looking at this routine here, and it looks like it's doing an erase and then draw. But there's very little actually being drawn in terms of software sprites on the screen. So let's advance through the game until we get to a place where there's more software sprites on the screen, I think, and then we'll be able to conclusively deduce on how this game precisely renders its software sprites. So 2731, don't forget, is the in hex, is the start of plotting pixels or erasing them in bitmap memory. So we'll need to remember 2731 later on, but we'll remove all of the breakpoints, and then we'll advance through the game until we get lots more memories on the screen. There we go. Right, now let's put a break at 2731 again, and then let's see what happens. Pay very close attention to the debug bitmap view there in the graphics map window. Because we're in the erase and draw routine, and we have a breakpoint there, every time we start, there we go, we seem to be every time we start this routine, either something will be erased or something will be drawn into the bitmap. And that enemy there was just erased, and now it is being drawn. Interesting. So that enemy was erased and then drawn, and it was doing that in chunks of characters, 8 bytes at a time. That one is now being erased and then being drawn in a new position. So this routine erases and draws entire game objects at one time, by the looks of this. And it looks like each game object is going around in strict sequence. So the game, by doing this, minimizes the time that something is being erased and then redrawn. It's not erasing everything and then drawing all of the game objects in the next cycle. It's erasing a game object and drawing a game object one at a time. So it minimizes the time that something is not being displayed, or it minimizes the flicker on the screen. There is still going to be some flicker on the screen because it doesn't use a double buffered bitmap. Or it doesn't use two buffers of bitmap, rather it only uses one bitmap. So there is still going to be some time where the scan from the emulated display or from the CRT display, as the scan from the CRT display scans down the screen and draws the bitmap, there's going to be some time, some slightly less common or rarer situations where the bitmap data is not completely drawn, or when it's erased before it started redrawing the enemy. But that time is minimized by erasing and drawing in game object sequence, rather than erasing all of the game objects and then drawing all of the game objects. This game stands out because you can see that there's a lot of hardware sprite frames for the player ship. In fact, there's 2 rows there, and each row is 16 frames, and that's 32 frames in total. We have quite a variation in terms of the cloud sprites, and there's some explosion sprites. We have the person in with the parachute, and then we have some score updates, and we have other explosion frames as well. So this game is actually pretty cool, right? I mean, I do like the way that this game has been put together. Maybe if I was coding it, maybe I would not have used the self-modifying code for erasing and plotting bitmap data. I might have optimized it a bit more by having 2 routines, one which does the erase and one which does the draw, and I might have done it that way. But apart from that, this game is pretty optimal. I might have used a double buffered bitmap as well, which would have complicated the erase and draw routine, because then you'll have to store the 2 positions, right? At least, I think, maybe, maybe 3. No, 2 positions. You'd have to store the previous position for the position that you'd have to draw, because you're using 2 double buffered bitmaps. But yeah, I would have minimized the flicker by having a double buffered bitmap. But yeah, I wouldn't have used self-modifying code either, because you're wasting CPU cycles by doing those no-ops, right? I would have had 2 routines, one for erase and one for plot. But apart from that, this game is pretty much how I would have approached it. I mean, the clouds, the expanded sprites being used for the clouds, plus the player, plus the person with the parachute, and also the score, for example, the score display, hardware sprite frames. Yeah, I would have done pretty much the same way of writing this game. So pretty good, good job, Henrik, on writing this game back when you did, many decades ago. We can see, actually, if I've paused it and I'm single stepping through now, we can see that it's taking 4 frames to render each game update when there are many enemies on the screen. That's quite a number of frames, right? The frame rate on this game is not the best, but it's actually really good, right? Considering how many sprites there are on the screen, how many software sprites there are on the screen. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.